So in this video, we're going to talk about the theory behind variation in parameters. Why does it happen? Why does the system come out that way? So let's suppose we're starting with a second order differential equation and it's written that way. So this is non-homogeneous and we need to put it in proper form. So if we divide everything by a sub 2 of x, we end up with y double prime plus a new function which we would call p of x times y prime, plus a new function here when we divide. I'm going to call it q of x times y. And then we're going to have a new function over here, which I'm just going to call f of x. So we're asking a simple question. We know how to find the complementary solution, right? We would take y double prime plus p of x y prime plus q of x y and set it equal to 0. And when we do that, since this is second order, we would end up with two functions that would satisfy that. A y1 of x and then y2 of x. I'm just going to call them y1 and y2 later for short. So then our complementary solution would look like c1 y1 plus c2 y2. We are asking the question, is it possible to replace these coefficients with variable coefficients or with functions? I'm going to call them U1 and U2. So since they're not constants, we would call them variable parameters, such that the particular solution would be U1 Y1 plus U2 Y2. Is that possible? That's what we're asking. Well, let's see what would happen. So we've got the yp in the form that we would want it in. We know usually what happens is we take derivatives, substitute it into the original equation. So let's find some derivatives here. If I find the derivative of yp in this format, I'm going to use product rule. So it's first function times derivative of the second plus second function times derivative of the first. And then I'm going to do the same thing with that second term. First derivative of the second plus second derivative of the first. And just to be consistent, I'm going to write my u1s first and my y terms second. And then we need to take a second derivative. Since this is second order, we want to substitute a second derivative in there. So yp double prime, same thing. We're going to use that product rule. So it's going to be first derivative of the second plus second derivative of the first. Second term, same way. First derivative of the second plus second derivative of the first. Third term, same way. First missing the prime there. Derivative of the second plus second derivative of the first, and then that last one, first derivative of the second plus second derivative of the first. I'm just going to take a moment and make sure I have my primes in the right place. So we've got things we can substitute into this derivative, or into this differential equation. So our differential equation, remember, is y double prime plus p of x times y prime plus q of x. Y is equal to f of x. So we have y double prime. So I'm substituting in here. Now I know I could combine those. I'm going to leave them separate because I'm going to have to reorder some of this stuff. Let me just make sure I've copied everything. So I've substituted in y prime, double prime. Now I'm going to substitute in y prime. So we have that function p of x times y prime, which we said was u1 y1 prime plus u1 prime y1 plus u2 y2 prime plus u2 prime y2. And then we have plus q of x times y. And our y was u1 y1 plus u2 y2. And we're saying this is going to be equal to f of x. So I'm just going to kind of work with this side right now, because eventually this is going to be equal to f of x. So I've just substituted in there. But I want to clarify and kind of condense some stuff here. So let's look at all those terms that have a u1 in them. So I'm going to do some rearranging here. So I've got a u1 term here, a u1 term here, and a u1 term here. And I'm trying to make some of this look like something that I already know. Something in terms of what that complementary solution was. That way I can cancel some things out. So if I were to write that, I would have, and I'm going to factor that u1 out. And that's going to leave me with y1 double prime plus p of x times y1 prime plus q of x times y1. And now I'm going to do the same thing with u2s. So I'm going to find my u2 terms. Here's a u2 term. Here's a u2 term. And then here's a u2 term. And I'm going to factor out the u2s. And that's going to leave me with y2 double prime plus p of x times y2 prime plus q of x times y2. So now I'm going to just rearrange some other terms here. So I'm going to have a u1 double prime y1 plus u1 prime y1 prime. And I'll explain why I'm going to arrange it in this specific format in just a few minutes. Plus u2 double prime y2 plus u2 prime y2 prime plus, and I'm going to do some grouping here. So if I look at what's left with that p of x here, I still have these two terms in there. u1 prime y1 plus u2 prime y2. And then I have a u1 prime y1 prime plus a u2 prime y2 prime. So I just did some clever grouping here. I grouped all the u1 terms together, factored out u1, grouped the two terms together, factored out a u2, and just rearranged everything that was left here and here. And this is the leftovers for my p. And remember, in the end, this is equal to f of x. So this is equivalent to what we just did. Now, thinking about that complementary solution, so I'm going to scroll back up a minute. When we found that complementary solution, we have a y1 and y2. And what we're saying is that that satisfies the complementary homogeneous differential equation. So that also is a solution to this particular differential equation, which is the non-homogeneous portion of the differential equation, which means that when we grouped the u1 terms together and were left over with this, that y1 was the solution to the complementary. It's also a solution to the non-homogeneous differential equation, which means that that guy has to be equal to 0. Same thing's going to be true here. That's going to be equal to 0 because it satisfies that differential equation. So we are left with just all of this fun stuff. But we can do some groupings here. We can group these two terms together and think about writing it in terms of a derivative. And then we can group these two terms together and think about writing them in terms of a derivative. So if we look at that first grouping here, we could rewrite that as if I were to take the derivative with respect to x of u1 prime y1. That would give me back this. And if I were to rewrite that second one, d over dx, this is equivalent to u2 prime times y1. If I take the derivative of this, I will get this guy back. And then we're left with all this other stuff. Now we could condense that and put those two together. So that's the same thing as saying I'm taking the derivative of u1 prime y1 plus u2 prime y1. Oh, just kidding. That's a y2. Let me correct that subscript. Okay, still a true statement. Plus p of u1 prime y1 plus u2 prime y2. I'm going to use a bracket there instead of parentheses. Plus u1 prime y1 prime plus u2 prime y2 prime. So that's equivalent to what we did above. So we are going to make an assumption now that this guy is actually equal to 0. Well, if that's equal to 0, then that means that's going to have to be equal to 0 too. Okay, which means that we're left with just this piece. Now remember, we said that in the beginning, that second order derivative can be written that way, and then we just made substitutions for y double prime and y prime here. So in the end, all of this is equal to just f of x, which means this guy is now equal to f of x. And if this is 0 and this is 0, then it stands to reason that this would have to be equal to f of x. And that is enough information to produce a system of equations. So here's the assumption that we made. U1 y prime y1 plus U2 prime y2 was equal to 0. And then it's followed that U1 prime y1 prime plus U2 prime y2 prime was equal to f of x. So that's where a system is coming from when we create that system. And that gives us enough information to figure out what our D matrix should be, the determinant of the coefficients. Remember, our coefficients here are y1 and y2, and then y1 prime, and then y2 prime. And then our du1 prime replaces that first column with 0 and f of x. And then our du2 prime replaces that second column. So now that you can find those determinants, then that means that u1 prime has to be equal to du1 prime over d, and u2 prime has to be equal to du2 prime over d, all by Cramer's rule. And then once we figure out what u1 prime and what u2 prime are, we can use separation of variables, and then we can solve that system. So then once you do that, you know what U1 and U2 are. Everything has to go back into that original assumption. The original assumption was that we could write this particular solution as U1 times Y1 plus U2 times Y2. So that's where the theory is for solving this would be a second order differential equation that way. We could branch this out to a third order, and you've seen in the other videos how to solve a third order. But that's where the theory is coming from. The important part is coming up with that system of equations, because once you get that system, everything else is really just finding determinants and just doing some basic calc integrals. So that's the theory behind variation of parameters.